like to introduce our first presenter. He is Travis Richardson, President and Chief Product Officer with Flywheel. Welcome, Travis.
Great. Thank you, Elizabeth. And thank you, everybody, for joining us today. We have an exciting discussion around the practical challenges associated with large-scale medical imaging and AI. Elizabeth has introduced me, so I'll say we're excited to have some exciting guest speakers with us today. Brad Genero joins us as he's the Medical Imaging Alliance Manager at NVIDIA, and Brad will provide some content on how NVIDIA's technology is supporting the project at Wisconsin. I will likewise provide a little overview of what Flywheel is and how we support the project as well. But our featured speaker is really Dr. John Garrett, who is the Director of Imaging Informatics in the Department of Radiology at the University of Wisconsin's School of Medicine. So we'll be focused on how they're addressing their COVID-19 research and applying kind of a research data management framework to develop AI algorithms at scale. The agenda this morning is we'll start with John giving us an overview of broadly AI in medical imaging and research, and then Brad will join us to talk a little bit about specifically how NVIDIA is supporting that work. I'll provide a little bit of an overview of Flywheel in that context and tee up a little bit of a discussion of where AI is headed. But then John will kind of wrap us up with tying everything together and talking about exactly how all of this was applied in a real-world use case. So with that, Elizabeth, I think we'll want to hand that over to Dr. Garrett.
Good afternoon, everyone. It's great to be here. Thanks, Travis and Elizabeth, for that introduction. I'm really looking forward to our discussion today. I think we have some exciting work to share, and looking forward to some Q&A at the end as well. Very briefly, before I start, I'd like to disclose that this work was supported by both the NIH and the Wisconsin Partnership Program. So I probably don't need to tell anyone who's sort of listening into this call today that AI or artificial intelligence is sort of the most hot topic in a lot of different fields, but in particular in medical imaging. And I really like this graph that we're looking at. This is showing over the last 20 years, sort of the count of peer-reviewed publications year to year, where both radiology and either artificial intelligence or deep learning appears in the title and abstract. And I think it's just a really striking trend in the last couple of years that we can see starting around late 2016, 2017, this just astronomical sort of growth in the sort of applications of AI or deep learning in medical imaging. And so one of the important questions that we can ask is, why is that happening today, that we're seeing this sort of explosion of publications? We're seeing lay press articles talking about why is deep learning changing your life, headlines that are really attention grabbing, AI versus MD. And I'm going to pause there because it's Doctor's Day today and just say right now that I, for one, don't see this as an AI versus MD problem at all. I think AI is really going to be a useful adjunct in medicine and in medical imaging in particular. So, but again, I think it's an important question. Why are we seeing this sort of hype and this excitement today? And technically, deep learning is relatively new, but machine learning techniques have been around for quite a while. In the early 1990s, they were being used in mammography for CAD, computer-assisted detection. But one of the challenges with more traditional machine learning tools is that you had to really be an expert and understand those tools really well. In the bottom right is one of my favorite diagrams that shows kind of the decision tree that you might take to find the right tool for a machine learning problem using a popular library, scikit-learn. And this is basically saying, walk through your data set. How many data elements do you have? What kind of problem are you trying to solve? Deep learning, which is really just in about sort of 2016, 2017 taken off in a big way, has changed the game for this in a lot of different ways. For one thing, you no longer need to be an expert in all of these different sort of sub areas of machine learning, provided you have adequate sort of data and compute. You can actually use, I don't love the term brute force here, but it's basically a one-size-fits-all method to try and solve many more problems. The other reason that deep learning has really taken off is related to two things. One is the sort of recent availability of large-scale data sets, and this is particularly true in medical imaging, where grand challenges hosted by groups like Kaggle or others have created these enormous data sets, and I think a lot of academic institutions and organizations are working to collect those data sets themselves. In addition, computing power has grown at a really astonishing rate, and many, if not all, deep learning techniques use graphic processing units or GPUs to do their computing. And just for some comparison, back in 2008, the so-called Tesla personal supercomputer was introduced by NVIDIA, where for about $10,000 you could put, 4 teraflops of compute under your desk, which compared to today, for under $2,000 you can build a workstation that's almost 300 teraflops of deep learning compute power to put under your desk, and so it's becoming just very accessible. So before we dive into our specific example focusing on COVID-19 today, I want to highlight a couple of areas where I think that AI is really making some great strides in both the research and sort of applied space in medical imaging. So in the first place that I want to sort of talk about is the applications of AI in what I'll call basic science research. And so this is fundamental physics or other imaging sort of tools that are being now augmented by the introduction of deep learning techniques. Some of the areas where this has been seen to show great promise or even actually already be in use is in the area, for example, of image reconstruction. Historically, image reconstruction has been performed by applying known physical models and mathematics to turn raw data into usable images for interpretation. This always requires both a deep knowledge of physics, but also some assumptions about those models. And AI has been used to sort of learn some of those gaps in those models and generate some pretty amazing results in CT, MR, and other modalities. One of the other sort of areas where this has been applied is actually learning kind of physical predictions or physical models where we don't have any analytical tools yet that allow us to sort of do that. And one of my favorite examples is shown on the bottom right here, where using deep learning we can actually learn how energy, the X-ray spectrum, is being encoded in a normal CT image and generate images as though we had acquired a multi-spectrum imaging, which typically requires dedicated or specialized hardware or unique acquisition protocol. But with deep learning we can now do this retrospectively on any CT study that's being performed. And finally, it's able to allow us to even translate between different types of imaging, such as CT and MR. And this may not seem necessarily like an intuitive application, except that there are a variety of systems, for example, PET-MR, where the combination of the PET imaging and the MR soft tissue visualization is really a great combination. But you need CT imaging to correct those images, and so generating pseudo-CT or synthesized CT from those MR data sets make that a really powerful system. One of the other areas that we've seen a lot of AI applications, and in fact this is where the most FDA-approved modules that use AI in the medical imaging space live today, is in workflow improvements. And this includes things like image triage, where maybe a head CT gets bumped up a priority list because AI suspects there may be an intracranial hemorrhage or cervical spine fracture. And this is really quite useful for potentially speeding up, how quickly those studies are seen by people, and also helping act as sort of a second reader, although in many cases that's not necessarily the on-label use for them. So one of the other areas where this has been used is for predicting patient no-shows and allowing organizations to optimize sort of how they schedule and utilize their equipment, limiting the downtime and being more efficient with their scanner resources. Another very popular task is to speed up imaging tasks that radiologists or other physicians are performing, but that are time-consuming, but not necessarily tremendously difficult. A great example of that is the interpretation of pediatric bone age studies. And to the right, we can see what an example of this might look like. But the traditional sort of method for reading these studies is that the radiologist or endocrinologist would interpret the X-ray by examining the bones and the structures and comparing those to an atlas of standard models for patients who are a similar age and sex. What AI has allowed that to do is to basically automatically make a prediction and provide reference images for the radiologist or endocrinologist to make that process much more efficient. And finally, a last workflow improvement that's really promising is the application of AI to improve patient positioning, which can help with both image quality and dose reduction and can be done on the fly while a patient's in the scanner. The last sort of area that I want to touch on before diving into our COVID-19 work is so-called opportunistic screening. And this is an area that's really just, I think, very exciting and really interesting, and started actually at UW, where one of our abdominal radiologists, Perry Picard, who has been leading the field in sort of CT colonography over the years, realized that in many of these CT colonographies, there are extracolonic findings that were not necessarily part of the reason why the scan was ordered, but could tell you something about that patient's sort of future health. So that work has led to a variety of now fully automated tools that from an abdominal CT scan can be used to assess things like bone mineral density, aortic calcifications, different types of fat, sort of segmentation in the abdomen, as well as muscle density and things like that to predict long-term outcomes for those patients, all basically getting this information for free because these exams are typically ordered for some other reason. So I'm going to shift gears now a little bit to a specific application of AI, and I'll try and sort of articulate first why it's a good application for AI, and then talk about some of the challenges in actually leveraging AI for this project. And so on the right, we can see a chest X-ray of a patient with COVID-19, and the clinical presentation for this has been well documented as most commonly showing patchy ground glass opacities or consolidations in the mid to lower lungs. However, this is really not a very specific sort of finding and can overlap with other viral illnesses, drug reactions, or even fluid aspiration. And so partly the reason that these sort of findings are not necessarily well understood, although I think this is getting better, is that COVID-19 is still a very new disease relatively, and many radiologists basically had to learn on the fly how to interpret these images and how to decide if this X-ray was indicating COVID-19 versus some other pneumonia. However, this type of classification task is actually something that machine learning methods have been shown to excel at in a variety of different applications. And so one of the really important questions that came up early on in the pandemic is whether or not a deep learning method could be trained to successfully differentiate COVID-19 pneumonia from other abnormalities on chest X-ray images. And so the initial kind of naive thought that I think many people might have is to say, well, it's very simple. We get a huge data set. We get a big powerful server. We can solve any problem with AI. We'll feed it a chest X-ray. We'll train it to give us a result, and that's all that it takes. But one of the huge assumptions that goes into that sort of enthusiastic sort of statement is that you really need to have ideal data for that to be possible. And so what we mean by ideal data here is that we would be able to find X-rays where we know why those X-rays were ordered. So maybe it's being assessed because somebody has chest pain, or maybe they're suspected of having COVID-19. We would need access to good quality data, imaging data specifically, so X-ray images that are consistently acquired. You'd need, tens of thousands of examples like this, and then you also need to know, is this a case where there's some ambiguity for the radiologist? Do they clearly know this is something else, or are they on the fence about what this may be? You also have to have ground truth confirmation whether this is actually a patient with COVID-19 or not. And that comes typically from the gold standard polymerase chain reaction PCR test. You need to know not only if that's positive or negative, but also when that patient had a test taken, is it a relevant test to the exam? If they had a test 2 months ago and then they have an X-ray today, is that a useful training pair or not? So in reality, the data are not quite so clearly laid out. Typically, the imaging is going to be found in a picture archiving and communication system, or a PACS system. One very good thing here is that the DICOM standard has really been well adopted. I can't think of any medical systems that don't use it for radiological imaging. And so these are going to be fairly high resolution images that will have good structured data available. But at any health system, there may be limited numbers, particularly for rare or novel diseases like COVID-19. You may also find that any given health system may not have good representation for different groups, which can lead to a biased data set. The other challenge that we sort of face is that we'd like to know, why was this study ordered, and how does the radiologist see this exam? Is it something where they have a clear picture of what it is, or is this a case where we actually need a tool like this? And unfortunately, that's not something that's going to be available in a binary sort of way. Instead, what we get are free text reports that are typically stored in a separate system, a reporting dictation system that the radiologists use. And if we look at the impression in this example report to the right, we can see that in this case, this is actually a great candidate for a tool like this, but it's not a simple, yes, we'd like a tool like this. Instead, what the radiologist says is basically this is features that are consistent with pneumonia, and COVID-19 is a possibility. Finally, for the ground truth sort of diagnosis, we need to have yet another clinical system, the electronic medical record, to be able to sort of search for patient history and find out, is this a patient who's been tested for COVID-19? When was that test? Any other demographic information we may need to know about them, and then is this test result, positive or negative? And that, again, particularly for new tests like were being developed during the pandemic for COVID-19, this is, again, an area where it may not be so simple as finding a test result and labeling it positive or negative. Just as an example on the right, these are the 4 different possible positive and negative responses that we found in our EMR indicating COVID was present or absent. So just to wrap up some of the challenges that we've talked about, for starters, when we're trying to collect data to solve a problem like this, we're pulling data from different data sources, including the PACS, the EMR, and a dictation system. And we need those data to be normalized. We need them to be consolidated and accessible all in one place. But one of the other challenges that we didn't talk about yet is what to do with those data, even when we get them sort of in place, because most of the time our first guess for a deep learning architecture that's going to work really well, or a data pre-processing scheme, is not going to be successful. And so instead what we need is to be able to access those data and try repeatedly to come up with a good model and a good sort of data processing pipeline. And finally, any model that's trained needs to be validated, not just presented as an AUC or something like that, an area under the curve, but it really needs to be validated against human observers and the ground truth. And so in order for any project like this to succeed, it's not enough to have a great idea or a really good problem, but you also have to have the infrastructure to handle and maintain those data, and computing and tools to make the training of those models portable and reproducible. So I'd like now to hand the presenter ball over to Brad to talk a little more about some of the computing and other tools that NVIDIA has to help address this.
Fantastic. Thank you so much. John, that is awesome. That is very awesome. So that is really exciting to see where we're at and what we can potentially do. And I'm happy now to talk a little bit about some of the tools that we go about to build some of these things. NVIDIA has been very active in the healthcare space for quite some time, whether it's around visualization, around analytics, or AI, or virtualization. We're there to help accelerate breakthroughs in healthcare and life sciences. So whether it's using our supercomputers, whether it's using our tools or SDKs, whether it's how we help to power the next generation medical devices, and how we enable the entire ecosystem, whether it's all the way down to an embedded unit inside of a CT or MRI, to a workstation for a data scientist, to a server that's processing tons of data for AI or visualization's sake, all the way up to the cloud. There's something that NVIDIA provides in each of those to help enable each of these ecosystems to do great things. When we look at our entire stack from bottom to top, it starts out from the data center layer, the GPU layer, the smart NICs, the networking. On top of that, whether it's our workstations, our computing at the edge, or up in the cloud, or all the different workloads on all these different places where we would choose to do this work. On top of that, we have CUDA, our programming language for the GPU, as well as our toolkits, our CUDA-X, to unlock analysis analytics across many different domains. So whether it's for healthcare, or for automotive, or for robotics, or for smart cities, these libraries are shared, benefit from everything that we learn from each of these different domains. We can apply then to the vertical specific areas. And so up here at the application framework level, we have our Clara toolkit, which is everything healthcare, being able to use the best and brightest of what we've built and really geared towards various domains within the healthcare space. And then from here, we're able to construct all sorts of applications using those SDKs. So whether it's in the imaging space, which is where I spend most of my time, if it's developing smart instruments, if it's using NLP, natural language understanding, or genomics or drug discovery, there's a set of toolkits that help to accelerate the development work in each of those areas. It comes in the form of creating and leveraging health data, and how do we take this into our development of AI applications, whether it's through our training frameworks, whether it's using techniques like federated learning, I'll talk about that in a couple of minutes, our deployment and inference platforms, or if it's leveraging a lot of the pre-trained models that we've created. There's something there that can help accelerate developers and data scientists in what they're creating. If I look now specifically at our Clara imaging framework, there's really four main components. There is, I'll start here at the AI-assisted annotation. This is where we take data that's coming from a PACS, a VNA, from a modality, and take that's unannotated and rapidly annotate it. Doing a manual CT annotation, if I, for example, take a kidney or a pancreas, if I'm going through slice by slice and drawing an annotation on top of that, that could take a considerable amount of time from a trained expert. Being able to leverage AI-assisted annotation to help accelerate that and create that annotated data that we could then in turn use for training our models is a big acceleration boost. We have our Clara Train, the training framework that has the ability to take this annotated data, whether it's for classifications or segmentations, and be able to train up a model or fine-tune a model and leverage things like determinism, which is really important in the healthcare space, as well as Automl to correctly find the right parameters to get that model out as efficient as possible. And then we have our deployment framework for running inference. This is where we can take that model that's been created and connect that up into a pipeline that you can connect a PACS or a VNA or a router and take that data in, process it, create results that could then be sent back to the clinical systems that understand DICOM or HL7 Fire or things like this. And the last piece on the far left is our pre-trained models. This is we have about 25 or so models that have been trained on publicly available data in various areas to help accelerate and spark developers in creating meaningful AI in their ecosystems. So whether it's on identifying the liver or the kidneys or brain tumors, or being able to classify conditions in chest x-rays, these are seed models to really start to demonstrate how you could actually use this framework in your own applications. On the training side, as I mentioned, if you go one layer deeper, we're currently based on TensorRT if you're following the frameworks, but we're moving to PyTorch, which is based on an application framework called Mri. So really optimized training. It uses things like AMP for automated mixed precision. It uses determinism to make sure that every time we train the model with the same data, we're getting the same model output. We're using transfer learning to do fine-tuning. We can take pre-existing models that could have been trained from one institution and being able to fine-tune it with data from another institution so that it aligns with the modalities, the firmware of the instruments that are run at individual sites. The data is tuned towards what we've trained the model on. We have federated learning, which is where we can train models without having to pool the data together in a centralized location. Because healthcare data is by design patient-centric and very sensitive, we don't want to just pool that all together in one big data lake if we can avoid it, because there's challenges with anonymizing and doing these sorts of things to get that data together. With federated learning, we can train a model together collaboratively where the training is happening at the local sites, but the model aggregation is happening in a centralized location. It could be at a teaching hospital, it could be up in the cloud, it doesn't matter. And then Automl, as I mentioned, these are ways that we can select the right hyperparameters for the models that we're creating so that if we don't know the exact right value, we can provide a range of values and Automl will work through and select the right ones for you. The pre-trained models that we have available, I mentioned a little bit on them. There's ones for spleen or liver or brain or prostate. We have an X-ray classification model. We do have several COVID models that are available for doing things like lung segmentation for COVID cases, or taking that lung segmentation and doing classification on it. There's also a model for oxygen prediction. So when a patient presents in the ER and has an X-ray done, what's the likelihood that they would actually need to go on oxygen? A model that's available that developers can download and experiment with. And then these models can be used both for our annotation as well as our training frameworks. Just deeper dive on how the federated learning works, whether it's, we're bringing together different hospitals into the mix, bring, very distributed data sets to be able to create that one model that works for everybody. So just, a quick wrap up. If you're interested in learning more, there's a ton of information that's available up on the web. So whether it's at our homepage, or if you want to go and download these models or the training frameworks or the deployment inference framework, you can start at ngc.nvidia.com. There's a number of development videos available up on YouTube and blogs. Follow us on Twitter. It's very easy to get started. So with that, I'm going to pass things over to Travis. Thank you very much.
Thank you, Brad. And I'm going to pick up here and just explain a little bit about Flywheel's role in all this. You've seen, sort of the need and the opportunity presented by John, and in terms of, just a vast array of potential for AI and medical imaging. Brad has outlined, sort of all the technology available to help you, train models and kickstart your projects and so on. But Flywheel comes at it from the data point of view. And I'm going to emphasize a little bit about, how we help there. So Flywheel, if you're not familiar, is a data management platform for biomedical research and collaboration. Fundamentally, it's a software informatics platform that helps you scale, collection and management of data to support various research initiatives. So it could be imaging research and maybe a population study of some sort that involves lots of imaging data and various analyses. Machine learning, as we're talking about today, is a big driver for a lot of Flywheel adoption. And also because we're web-based and secure and so on, we're actually really useful for multi-center studies where you're perhaps collecting data from multiple sites and collaborating on data with partners in different locations around the world. And, if you kind of look at the heart of Flywheel, it's about, capturing data, imaging certainly, but Flywheel was designed to be, to support, multimodal biomedical data. So, as John mentioned earlier, the idea of ingesting imaging, but also the EMR, PCR test results or radiology reports, that sort of thing. We're also doing work on digital pathology, ophthalmology, excuse me, EEG, genomics, other data sets. But broadly, pulling that data in, de-identifying that data as necessary, organizing it in a database that keeps track of, all of your metadata and helps you label things. And I'll come back into some more specific examples there. But essentially, large-scale management of biomedical data to support your various research initiatives. There's also a computational framework that helps you automate routine processing pipelines. So anything from basic pre-processing to quality control, as well as training runs or testing of your models in the context of machine learning. And of course, in Flywheel, everything is done in a framework around secure collaboration. So if you're in a research institution, you might think of this as IRB compliance. You have only the right people, only the right data, working on the same problem together, so you can, kind of control access and collaboration. And that's broadly what Flywheel is about. It's about, scaling research data management and enabling collaboration. And we work across academia, clinical, life sciences, and AI developers who are similarly, ingesting large volumes of healthcare data and trying to create new algorithms to add value. So that's what Flywheel is. Our vision broadly is to enable research collaboration, whether that's amongst research institutions or life sciences or together. Broad set of collaboration opportunities exist there, but certainly machine learning and federated learning are top of mind initiatives. We'll come back to that in a little bit. But Flywheel is pretty broadly deployed, and we're we'll describe. I think John will come back and talk a little bit about how Flywheel is used to help their COVID-19 initiative specifically. But broadly, why we're here is Flywheel is aimed at the problem of data management to support your machine learning and similar applications where, depending on who you talk to, you might hear a number as high as 80% of the effort is the data management. It's collecting the data privacy and security, dealing with the diversity of data types, quality, standardizing, labeling, tracking everything, the provenance necessary to support scientific reproducibility, the provenance necessary to support FDA approvals, things of that nature. And then, of course, regulatory compliance. You're dealing with, healthcare data, those, heavily regulated, and you have obligations in how do you manage the data that we can help with. So if I talk a little bit about machine learning specifically, I'll just hit a few examples of how we can contribute. First is finding useful data. As we'll talk about search and how you can organize data to help, populate new projects. Quality and consistency is important. It's as John pointed out earlier, it's sort of, what is the right data to support the training process, getting the quality right, the ideal data. The preparation of that data in terms of labeling, organizing, classifying that information so that the training algorithms can process it is also something we can help with. And then, of course, coordinating the data with the actual training and testing processes. So at a super high level, one key area where Flywheel helps is we can ingest very large volumes of clinical or patient data, imaging, non-imaging data, and then help our customers organize that data to support downstream reuse. So it could be in the form of existing projects. I want to repurpose some data. It could be organizing a data lake, a repository of research-ready data, and just organizing that to be drawn from for new projects like machine learning. It could be as simple as taking in radiology reports and putting some structure around that data. But one of the key capabilities in Flywheel is a very powerful search engine that allows you to select from that data and create new projects to support downstream applications like machine learning. An example, Dr. Garrett alluded to this kind of thing earlier, where you might get some raw text as an input on the left, a radiology report, kind of just a human being writing some findings or documenting their read, but it's not structured in a way that wouldn't necessarily help you with search or some kind of quantitative analysis. So a common example of maybe where you could use Flywheel's gear functionality, and gears are our terms for containerized workloads that kind of automate the computational processing, might be to use a natural language processing module. In this case, I'm illustrating a traumatic brain injury related gear that we've implemented that reads the radiology report on one side, and then on the right, and hopefully you can see this, it identifies, I think, 27 different pathologies and whether those pathologies are present or absent explicitly. So it's interpreting the text on the left and giving you structure on the right, which then supports the searchability. So you can go in and say, I want to find people who have some specific combination of pathologies, absent or present, and you can find more results and get where you're going. Another key element is just assessing the quality, and so common use case for Flywheel would be to run quality assessments on the data as the data arrives. So here's an example using a popular application in the neuroimaging world called Mri Qc, and it can ingest DICOM data and essentially analyze that data and provide a large number of metrics that assess the various quality, like signal to noise ratios, things like that. And then it also generates, in this case, visual reports that make it very quick and easy to visually inspect the data and see that it meets your needs or not. So the approach of quantifying those metrics and providing visual inspection can be very powerful in speeding a quality workflow, for example. Image annotation, Brad alluded to this. It's an important element in the workflow. So Flywheel has built-in visual viewers for visual inspection, but you can also configure those for image annotation and the workflow associated with blind reader studies, for example. So you have the ability to configure which ROI types, regions of interest, which tools you want to use for annotating the images themselves. And you can also create a qualitative summary form. So as the radiologist reads each of the data sets, and you can structure their response so that you answer very specific questions and can quantify the results at the end. And all of that is databased in Flywheel and API accessible, searchable, and helps organize your labeling and annotation workflow again, all as input into the inputs to the machine learning process training. And then broadly speaking, Flywheel, because of its computational framework, it can help with the overall workflow. So we've talked about a number of ways we can help you, select cohorts and prepare the data. But again, Flywheel's role is really just in the data management side of it. So, we're somewhat agnostic about exactly which tools you use to train. As Brad just pointed out, the NVIDIA tool suite is very powerful, particularly from our point of view in medical imaging. So our focus is getting the data organized and ready, and then sort of orchestrating the handoff into to the training world, with tools like the ones that Brad outlined. And then, of course, the models can be returned. We have tools for tracking the provenance of each training run, and of course, you can apply those models inside of Flywheel to test new cases and document the results of those. So again, it's designed to help you organize the data and orchestrate with the other tools that you need to train and test. I'm going to touch base quickly on federated learning. Brad mentioned this, and I think this is a very exciting topic in the context of where's all this going. On one hand, as John mentioned, the cohorts for many applications, can be very large and need to be diverse, potentially across multiple locations. And in order to train an algorithm that's generalized enough to be applied in a real world healthcare scenario. Yet data privacy challenges still exist. Many institutions are more than happy to collaborate on the development of new algorithms that advance healthcare, of course, but people are sensitive to selling people's private information. How do you deal with this? So the machine learning holds great promise for healthcare, better care at a lower cost, for example, and the concept of federated learning, as Brad outlined, is a very powerful idea. The idea that you could send an algorithm over to glean some model, a model and weights to be contributed to a broader model from the data, but not necessarily have to share the data or expose the data, and the associated risks. So federated learning is something that's definitely growing in interest. And the way we see it from a Flywheel point of view is the idea of the data management associated with that. How do you get the data from the various clinical and patient-oriented operational systems and protect it, but make it available for processing in an environment where the powerful tools that Brad outlined from NVIDIA can be applied. And so we're partnering up with folks at NVIDIA to make sure we can provide the data and leverage the powerful tools that Brad outlined. And John will come back here, I think, in a few minutes and talk about sort of how all these pieces fit together in the context of their COVID-19 research. But we're very excited about the possibilities for applying artificial intelligence at scale and helping these organizations scale and manage the data management challenge associated with making it a reality. So with that, I'll turn it back over to John and let him bring everything back together.
Thanks, Travis. And Brad, it's back to me, and I will go ahead and wrap us up today by going back to our COVID-19 example and talk about what we actually did for this project and how we were able to sort of leverage these tools to have some nice results. So with no further ado, I'll talk about our data set creation. I mentioned before that these data sets can be really large, and in this particular study, we ended up collecting close to 12,000 studies. These data were acquired actually not at UW. We were fortunate at the point when we started this project to not have seen so many patients in Madison yet who would have been sort of eligible for this study, and so we worked with a partner academic site to collect these data sets. In order to have the data be sort of fair, we collected all of our non-COVID cases were chest x-rays that were acquired prior to the end of 2019, at which point no COVID-19 patients had yet been seen. These were also then whittled down to only chest radiographs where the radiologists indicated that there was pneumonia detected on those exams, and that was done using a commercial natural language processing tool. For our COVID-19 positive patients, we also again only included frontal chest radiographs, and our gold standard for this was a real-time polymerase chain reaction or RT-PCR test result for COVID-19, as well as a sort of a radiologist diagnosis of pneumonia for these patients. And I will I'll say here that these patients that were included were only patients where they had an RT-PCR test confirmation either 5 days before or 14 days, other way around. So the RT-PCR could not be any more than 5 days after or 14 days before this radiograph was performed. This is a little bit of a busy slide, and I don't expect to have anyone read too much of what's on the right, except maybe if you watch this later on demand. But what I'd like to highlight here is that how we broke down our data and split it into testing and training data sets, as well as how we grouped it. So in this cohort, we had actually 6 different device manufacturers represented. 2 of those vendors we lumped together and called them V0, but just because they comprise such a small fraction of the total studies, and the remaining 4 were labeled anonymously as V1, V2, V3, and V4. We used 5,236 total images for training and validation and reserved 5,805 images for separate performance evaluation. So I'll briefly just sort of summarize some of the statistics of the cohort that was included. The average age in the non-COVID and COVID populations was very close, 62 versus 64. And then on the right side of the screen, you can see the sort of delta days distribution between the day of the PCR test and their radiological examination. The majority of studies did have a same day sort of test and image, with the sort of tails tapering off as we see. To the left, we can see the distribution of vendors. Again, a really nice split between the positive and negative cases for most of the vendors. And then on the right, I think this is worth mentioning as well. The data were collected including both computed radiography as well as true digital X-ray imaging, and that's the distribution we see there. So all of the data that were collected and curated for this project were aggregated at UW using the Flywheel platform. As Travis has already spoken at length about, this gave us a really nice way to both sort of poke around at the data and through a browser, just a Chrome browser on our desktop or something, audit the images, make sure that the quality and everything like that was okay. It also allowed us to add our own custom metadata where we can see the sort of red bars underlining our sort of custom data elements here, including that delta days between an exam and a positive test, whether COVID was detected, whether pneumonia was flagged, and whether that patient had undergone a PCR test. In addition, we were able to use the platform to generate various manifests for different training batches as we worked through this project, and depending on the tools that we were using, we were able to export those as either CSVs or JSONs. So to summarize the data set that we were able to generate for this project, it was a multi-center, so 5 different hospitals, and the multi-vendor data set that successfully aggregated the DICOM images along with the data from the EMR and the radiology dictation platform. And in an effort to avoid bias, the positive and negative cases were collected from the same hospitals and the same distribution of vendors. So I'll quickly go through our network architectures that we landed on for this project. We did try a variety of different tools and network architectures, but eventually settled on an ensemble of 20 individually trained DenseNet 121 deep neural networks. We performed a 3-stage transfer learning approach where we started using the ImageNet dataset, which has many millions of images and many 1,000 or so classes, and then subsequently trained on the publicly available chest X-ray data set from the NIH to refine and sort of teach the networks a little more about what chest X-rays look like. And finally, we did our final training on our COVID-19 data set. Each of the networks in the ensemble was trained using the same hyperparameters with random initializations, and the validation set for each network was randomly sampled from the total training data set. The quadratic mean of prediction from each of these models was taken to give the final prediction score, and a threshold of 0.3 was used to determine our positive versus negative diagnosis. And all of this training was performed using an NVIDIA DGX1 GPU server and anywhere from 2 to 8 GPUs at any given time. The data were actually cached on a local RAID array to speed up training, and we did use NVIDIA's PyTorch Docker containers from their NGC repository, which made it really easy for us to iterate over different network architectures and things like that. So on to some results. Our test set, we mentioned before, was almost 6,000 images. This was from 2,200 or so patients who had never been seen in training. None of their images had been seen as any part of the training. And the overall area under the curve, actually it was around 0.92 for this test data set. And we can see in the bottom two plots on the right that the performance was quite consistent across vendors and across different hospital systems, with a range from about 0.9 up to as high as 0.96 for the area under the curve. Because we had the ability to sort of adjust our threshold for this, we also were able to operate at either a high sensitivity or a high specificity point on the ROC curves that we see here, yielding a maximum sensitivity of 0.88 or a maximum specificity of 0.89. In addition to this sort of traditional results of just looking at the AUCs against the ground truth, we also compared this to the actual performance of experienced thoracic radiologists, including a radiologist from UW as well as 2 from Henry Ford. For this study, we asked them to read 500 randomly selected chest x-rays from 500 unique patients, 250 positive and negative exams. And you can see that the 3 readers sort of performance in the plot to the right. The AUC generated for those 3 readers was about 0.85, and on the same data set we actually achieved 0.94 from CV19net. And against all of the different readers, the p-values were statistically significant. In addition to providing a simple probability score for these images, we were able to generate so-called gradient class activation maps or GradCam heat maps shown to the right. The purpose of these is to try and indicate what features the networks are using to make these decisions. And actually in the 2 examples to the right, these are 2 cases where the radiologists, all 3 of them, made the incorrect diagnosis on these images, whereas the CV19net was correct. These features may be useful in helping radiologists learn to identify key characteristics or to sort of make these models a little more transparent, though I would say that there's still quite a bit of work to validate that process and really justify that these are telling us what models are using to make their decisions. This study did have some limitations. The data were collected during the early peak last year of the COVID-19 pandemic, and so the data set that we generated, of course, does not represent the true prevalence of the disease. In addition, we included multiple images from the same patient that were acquired longitudinally. We did do a follow-up study to this, actually, where we limited the data to only a single image per patient, and it didn't change overall performance, but in the presented results here we did. And finally, we really need to assess the sort of model's performance at other sites and on different data sets. So one sort of closing thought that I'd like to present, this is an article that was published about 2 weeks ago in Nature Machine Intelligence, where a group of computer scientists from Cambridge did a meta-analysis of papers that had been trying to apply AI to COVID-19 imaging, both radiographs and CT scans. And in this work, they started with a list of over 2,000 papers, so we clearly are not the only ones who had the idea that we could leverage AI to try and, combat this pandemic. But out of those 2,000 plus papers, they found that only about 7 papers total ended up using an adequately sized data set, more than 2,000 data points that were balanced for positive and negative cases, and actually only 4 out of 2,000 plus papers included large and balanced testing data sets as well, so not just for training, but for actually evaluating the algorithm. And we were quite proud to see that our paper had sort of met their criteria for this. And I think that this really emphasizes just how important it is to have infrastructure to allow you to collect and sort of manage these data sets at scale. So just to wrap up quickly, we presented our work showing that a deep learning method called CV19net could be used to differentiate between COVID-19 and non-COVID-19 pneumonias quite well. It actually exceeded the performance of 3 trained thoracic radiologists at this task, and our hope is that this can be used as an adjunct to potentially improve their accuracy and the timeliness of interpretation of these exams. And we're currently working to deploy this at UW-Madison and UW Health. In addition to having sort of positive results for this study, though, I think this is a really nice use case to emphasize 2 of the real requirements for success in any AI project. The first is that if you have the ability to quickly and easily curate and normalize data from many different systems, then you're going to be able to do work that's going to be much more impactful and likely generate more comprehensive and unbiased data sets. And finally, you have to have the computing tools and infrastructure to rapidly iterate through various architectures and pre-processing methods to do this well. So with that, I'd like to thank you all for your attention, and we'll move on to some Q&A.
Great, John. This is Travis. I see, just looking at, I know we're running short on time here, but I see a couple of questions that have to do with your data architecture at Wisconsin in terms of whether you're pulling data into Flywheel or you're pushing data into Flywheel. Maybe you could comment on how you're doing that and then sort of how you're setting yourself up for reusing that data.
Sure. So this workflow for us was a little bit unusual because we were collecting data primarily from other sites for this project, and we our implementation of Flywheel is actually 100% on-premise. It lives on our servers behind our firewall, which is very convenient for accessing our own systems, but less convenient for inviting collaborators so far, and that's a choice that we made when we deployed the system. But in the case of our work with Henry Ford, basically they shared their data in a what I'll call a pretty raw format. So we were basically getting zipped archives full of Excel sheets and DICOM objects, and we were ingesting the data using scripts that we had here, as well as some of the Flywheel command line tools and things like that. One of the reasons I think on one of my slides I had shown kind of how we were labeling the data, and we really tried to add all of this custom data, metadata that we were adding to these studies in as general a way as possible, because it is our hope that any data that we use for a project like this can be, for example, added to existing data sets like the NIH CHESS data set or the CheckSpert data set, other publicly available ones, and repurposed not just for the specific question that we were trying to answer here, which was, can we differentiate COVID-19 pneumonias from others, but for other classification tasks and things like that.
Right, and John, maybe I can just add, since I know part of the answer, just more broadly, your use of Flywheel is that you guys are identifying cohorts, pushing them into Flywheel, but setting them up so that they can be reused in the way you just described, so that you can draw from those and repurpose data for subsequent projects as needed.
Nope, I agree that is the case, and I would actually say not only are we doing this sort of for new projects that are ongoing, but one of our big efforts since we deployed the platform has been to sort of go back through old data sets that we've put together in the past and try and use Flywheel to normalize those, and pull them off of all the dusty hard drives that are sitting in students' cubicles and things like that, and put them somewhere where people can actually get to them, and if they have a question they'd like to try and answer, access those data and get to work.
Right, and so thank you, John, and Brad, thank you very much. Would you like to offer any closing comments at this stage?
All I can say is it's incredible the work that John and his team have put together. I think it's pretty amazing, and I think that really with the tooling, with the platforms that Flywheel has, I mean, there's really no stopping some of the incredible things that we're able to do, and it's just such an exciting time. And if there's anything, reach out on the URLs, reach out to us. Happy to answer any questions offline. Let's go on and do great things.